Okay, we're going to talk a little bit about balancing redox reactions, but before we get to that, we're going to do a brief review of oxidation reduction reactions. If you need a more detailed review, go back and watch my video on oxidation and reduction back when we were talking about chemical reactions in the first semester course. But for example, if we react zinc with hydrochloric acid, we'll eliminate the spectator ion chloride so that we can look at this reaction and more easily see what's oxidized and reduced. We have zinc reacting with 2H plus to form zinc ion and hydrogen gas. That is, the oxidation number of the zinc has gone from 0 to 2 plus, and the oxidation number of the hydrogen has gone from +1 to 0, because remember, elements that are free elements are 0 in terms of oxidation state. So the zinc has been oxidized to zinc +2, while H plus is reduced to H2. Notice moving in number lines. If you're going from more negative to 0 or positive, you're talking about oxidation. If you're going from positive to less positive or to negative, then you're talking about reduction. Now, since H plus causes the zinc to be oxidized, then it's considered the oxidizing agent. And since zinc causes the H plus to be reduced, it's considered the reducing agent. Note that the reducing agent is oxidized and the oxidizing agent is reduced. Again, look at chapter 4 for a little bit more detailed review than that. Just as a means of review, since we're going to calculate oxidation numbers to balance reactions, here's a couple for us to work on. And we'll apply the rules that we talked about in the first course, and then we'll work forward from that. So we'll do potassium permanganate, and we'll look at chloric acid. And so we have rules. Ionic substances, if it's a monoatomic ion, the oxidation state's equal to the charge on the ion. Oxygen tends to take the oxidation state of -2 with very few exceptions. And then we can solve for that and say we give it a variable x. So then essentially 1 plus x plus 4 times the -2, because there's 4 oxygens, adds it to be whatever the charge is. In this case, it's uncharged, so 0. And so x is going to equal +7. So the oxidation state on that manganese is +7. For the chloric acid, hydrogen's +1, oxygen again is -2. We don't have a rule for chlorine, so it's going to be 1 plus x plus 3 times the -2 is again equal to 0 because there's no explicit charge shown. I circled oxidation states so they don't get confused with charges. And so x is equal to a +5. And so that's how we look at the oxidation states and figure out what they are. Again, review of that is back in chapter 4 in the first semester material. So looking at this reaction, let's figure out what's being oxidized and what's being reduced. Usually, if I see metals in a compound, an ionic compound, and then I see it by itself on the product side like I do chromium, it would stand to reason that it's being reduced. So we got chromium there being reduced. Aluminum's going into an ionic compound, so I would assume aluminum is being oxidized. Now, if we look at the ionic compounds, the aluminum is going into a compound. Aluminum forms a +3, so it's a 0 as a free element and a 3 plus in the compound. because it's in group 3A. And we can see that that's true. 3 times minus 2 is minus 6. 2 times plus 3 is plus 6. That definitely works out. The reverse is true of the chromium. That's minus 6, just like before. So 2 times plus 3 should even it out. So we got 3 plus here, and it goes to a 0 there. So remember, the oxidizing agent is reduced and the reducing agent is oxidized. So the oxidizing agent is the chromium and the reducing agent is the substance oxidized. So that would be the aluminum. And again, that's a bit of a review from chapter 4. If you don't get that, go back and watch my oxidation reduction video from chapter 4. Now let's get to the balancing of the redox reactions. Remember, we got law of conservation of mass. That means we have to have the same amount of each element on both sides of the reaction. That's how we've balanced reactions up until this point. But the law of conservation of charge says that the electrons are not lost or gained either. We have to account for where they go. So if the reactions are more complicated, unlike the zinc and hydrogen example, we're going to have to use a little bit more sophisticated method. It means we're going to have to account for those electron transfers. Sometimes it's worth thinking of them as separate reactions or half reactions. And we're not going to focus on the half reaction method in this particular video, but it is convenient to look at those when you're keeping track of the electrons. We're not going to start from half reactions and build the reaction. We're going to start with the built reaction and balance it in this video. And so we separate into reduction and oxidation half reactions. So if we got 10, 2 plus reacting with iron 3 plus, producing 10, 4 plus, and iron 2 plus. Notice I need 2's on the iron to balance the electrons, not the irons, but the electrons, because iron is going to lose, or going from plus 3 to plus 2 is going to gain 1 electron, where the 10 is losing 2 electrons. So I need 2 irons losing 1 electron or gaining 1 electron to even out for the 10. And so to get the electrons the same, we have to have 2 irons. And that's not necessarily needed to balance the material, but it is required to balance the charge and the number of electrons. So if in oxidation, the electrons are considered products, and in reduction, the electrons are considered reactants or reagents. So notice the iron is being reduced, and so the 2 electrons is a reactant, and then the 10, it's an oxidation, so the electrons are listed as a product. So here are the steps to balancing a redox equation that already exists, not building it from the half reactions. We're going to assign the oxidation numbers to each thing in the equation so that we can figure out the number of electrons lost or gained. Determine the simplest ratio that's going to get our electrons to balance. Use those on the coefficients of the reactants. Keep in mind the number of atoms, like for example that iron, I needed 2 irons doing that to get the electrons to balance. And then I can balance the remaining by inspection. Usually there's going to be water or a salt or something that doesn't contain the atoms involved in the redox. So we'll look at 2 different reactions. Nitric acid reacting with H3SO3 going to nitrogen monoxide, H3ASO4, notice the difference in oxygens, and then water there to balance the hydrogen and the oxygen. And then the second one, we'll look at copper reacting with concentrated nitric acid, produce cupric nitrate, nitrogen dioxide, and water. So we'll look at each of those in turn. So let's get the ones we know. Hydrogen's ionic, so it's going to be +1. That's going to be -2. We'll have to figure this one out. +1, -2. Figure that one out. -2. +1, -2. We got a rule for those. That's plus. Hydrogen's generally +1. Oxygen's generally -2. Then we got +1, -2. So what we don't know is the nitrogen and the arsenic, and so those are the ones we have to figure out. So we got 2 times, that's going to be minus 6, plus 1 is minus 5, so this will be plus 5. That's going to be 6 plus 3, so that's going to be a 3. Minus 2, so this will have to be a plus 2. 4, that's 8, plus 3 is 5. So we got plus 5. So now we've got all the oxidation states. If you look at it, the nitrogen is going from plus 5 to plus 2, and the arsenic is going from plus 3 to plus 5. So this one is an oxidation worth 2 electrons. This is a reduction worth 3 electrons. And so we have to get that to balance. And so what's the smallest number both those go into? 6. So 2 times 3 is 6, 3 times 2 is 6. So 2 and 2. And then that's going to be 3 and 3. So that balances the electron transfers, but what I have to consider is the hydrogen and the oxygen. So I'm going to have to put a coefficient in front of water that will balance the whole thing. And so let's look. We're going to have hydrogen, there's 2 of them there. There's 9 of them there, so there's 11 hydrogens. 2 times 3 is 6. 3 times 3 is 9, so there's 15 oxygens. Okay. Hydrogen, there's 9 from here. But then I need to get the rest from here. Looks like I would get 2 from there as is, so hopefully the oxygens will work out as well. And so then the oxygen was 15, so I've got 2 there. 3 times 4 is 12. Plus 2 is 14, plus 1 is 15. So that balances, leaving a 1 coefficient there. So that reaction is a balanced redox reaction. But notice that the additional step of having to balance the charge out. Now let's consider the second reaction, the reaction of copper with concentrated nitric acid. We know that's 0 because it's a free element. -2 plus 1, -2. This is cupric nitrate, and so we can say that's a +2, -2, +1, -2. And so then balancing the rest, we did that one up here, so we know that one's +5 without redoing it. And turns out nitrogen in a nitrate is +5, but we'll go ahead and look at it. So if you got 3 times 2 is 6. For nitrate to be -1, this is going to have to be +5. And then this would be +4. And then we got all the oxidation states. So copper is going from copper to copper +2. So that is an oxidation of 2 electrons. Now the nitrogen that we're interested in is going right there. There is some nitrate that does not change oxidation numbers, so that adds a little wrinkle to this one. But regardless, it's a reduction by 1 electron. But I have to account for this one as well. So looking at it, it's a 2 to 1. Now, let's consider this a little bit more carefully because I've got the difference here. So what I would have, and so I switched to quality pencil because I'm going to have to change it. And so I would have to put a 2 there and a 2 there. Now, that balances the charge, but it doesn't balance the nitrate, because there's two there, there's 2 there. So what I'm going to do is change this coefficient to a 4 to balance out the nitrogen, because I've got to balance the material and the charge. So when I did that, it balances the nitrogen. The copper is already balanced, so I just have to consider the hydrogen oxygen. So hopefully I can balance it by just adding a coefficient here if needed. So that's 4 hydrogens there. And then, so that means I would need a 2 there to balance it. Now what about that? So I've got 4 times 3 is 12. And then I've got 6 there. I've got 4 there. Plus 2 there would be my 12. So that balances it. So I can go ahead and fill this in with ink, and that would give me a balanced reaction. Sometimes it's better if you think you might have to change a coefficient, work in pencil, even though I tend to work in ink on these videos to make it show a little better. And so that's balancing redox reactions.